Thank you. Thank you. The question of whether or not life exists beyond Earth is one of humanity's oldest, and I would argue most profound, and yet unanswered questions. And the search for life beyond Earth is, in part, the story of this lonely little planet reaching out into our solar system, searching for possible signs of life elsewhere. We've been undertaking this exploration for just over 50 years now. And through that exploration, we've just begun to understand not only which worlds out there might be habitable, but we've also begun to better characterize how our own planet sets bounds on the habitability for life as we know it. Now, what I'd like to focus in on are some of the worlds that we've come to appreciate just within the past 10 to 20 years, which on the surface, you might not expect that these are habitable worlds, but when you get to understand what's going on inside, it turns out that these worlds like Europa, Ganymede, Callisto, Titan, Enceladus, and even Neptune's curious moon, Triton, these are the worlds that I like to refer to as the ocean worlds of our solar system. Shown here, of course, at the center is the Earth, the ocean world that we know and love the most. But around the Earth, I've placed these icy worlds of the outer solar system, moons that are covered with ice, yet beneath their icy shells, we have very good reason to believe that vast, potentially global, liquid water reservoirs exist. And these ocean worlds of the outer solar system are really transforming our understanding of what it means for a world to be habitable. In the early days of astronomy and planetary science, we had this sort of Goldilocks scenario for habitability. The Venus, Earth, Mars system defined what it meant for a planet to be habitable. In order for a world to be habitable, you had to have a nice liquid water ocean on the surface in contact with an atmosphere. And in order for that condition to be satisfied, your world needed to be at just the right distance from the parent star, in our case, the sun, such that you had enough energy from your parent star to maintain that liquid water ocean on the surface. If you were Venus, you were too close and you got too hot. If you were Mars, you were too far away and you were too cold. But if you were at the Earth-Sun distance, you were right at that Goldilocks sweet spot for habitability. But these moons of the outer solar system, they're giving us sort of a new Goldilocks. And no place is this better exemplified than at the Jovian system, where Io, shown here, kind of takes the place of Venus. Io is the most volcanically active body in the solar system. What you're seeing in the inset and the upper part of Io there is a volcanic plume, a volcanic eruption occurring on Io. Io is more volcanically active than the Earth. There are likely volcanoes erupting on Io right now. And Io is so volcanically active, not because it's got energy from the sun. It's so volcanically active because of the tidal tug and pull that it experiences as it orbits Jupiter, which is some 318 times as massive as the Earth. And so in the Jovian system, we have this sort of new Goldilocks where maintaining liquid water is made possible not by energy from your parent star, but instead it's maintained largely by the tidal tug and pull, the mechanical energy of these moons getting flexed and stretched as they orbit Jupiter and Saturn and Neptune, Uranus possibly. And so in the Jovian system, we've got this new Goldilocks where Io is kind of like Venus. In the early days, Io may have had some water, but now it's lost any water that it once had. It's too tidally active. All the yellows, the reds, the whites that you see, that's all from these volcanic eruptions. And Callisto, at the outer end, though we think Callisto does have an ocean, Callisto's ocean is overlain by a very thick ice shell. And that ice shell is also very old, as evidenced by all those little pock marks on Callisto's surface. Those are impact craters, which to a planetary scientist indicates old age. But in the middle, we've got Europa and Ganymede. And Europa in particular, we think, may occupy this new sweet spot of the new Goldilocks zone, where it's got just the right amount of tidal energy dissipation to sustain this liquid water ocean in contact with a rocky seafloor so that it can have the elements and energy needed for life. And it's overlain by an ice shell that is maybe a few to as much as 10 or 15 or so kilometers in thickness. An ice shell that maybe provides a window into the subsurface ocean. These ocean worlds, of course, from an astrobiology standpoint, from a search for life elsewhere standpoint, are so compelling because if we've learned anything about life on Earth, it's that where you find the liquid water, you generally find life. From life in extreme environments like hydrothermal vents, the hot springs in the Rift Valleys, to Antarctica, from life in extreme environments to life of extreme lifestyles. All life on Earth depends on liquid water. But I'd like to show this image for another reason, and that is that part of the motivation, part of what underlies my passion for exploring these worlds, is that for all of the diversity of life on Earth, from the craziest of microbe in the deep ocean to the most bizarre of rock stars on the surface, all life on Earth is connected by the same tree of life. All of life on Earth as we know it is connected by the DNA, RNA, protein, and even ATP paradigm for how life works. I want to know, is there a different biochemistry out there? Is there a different way to get the business of life done? Is there a place in our solar system where life has originated independent from life here on Earth? Is there a second origin out there? And I think these ocean worlds of the outer solar system are the prime places to go and potentially answer this question. Europa, Enceladus, Titan, all these moons are so fantastic in the context of trying to answer this very primordial question. So what's next? Well, I'll begin with a little bit of my dream of dreams. In my dream of dreams, we send a highly capable lander to navigate to the surface of Europa. This would have to be engineered such that it could negotiate the canyons and the cliffs of Europa, find some spot on the surface where there are no rocks, icy rocks or boulders, put down the lander safely, and then deploy a melt probe. This melt probe would then have a heat source that allows it to go through this ice shell, penetrating through the many kilometers of ice, eventually reaching down to the ocean below. After that, it deploys the nose cone, and an autonomous underwater vehicle now navigates the ocean. Now, there's no joysticking this from JPL, so this little guy's got to figure out its way to the bottom of the ocean, and in at least this Hollywood version, this is an excerpt from Aliens of the Deep, an IMAX film I was involved with. In this Hollywood version, in the Dream of Dreams, we make contact with these charismatic macrofauna that, and that's not real, sadly. As I mentioned, this is my dream of dreams. Scaling back from that, we are at the shores of getting ready to hopefully set sail with new missions to worlds like Europa, sending missions that will fly by, look at the surface, take pictures, make chemical analyses, and possibly even use special radar to see the interface between the ice shell and the ocean. And then we'll send landers and melt probes and submersibles in the years to come after that. But part of what I get to do at the Jet Propulsion Lab and with NASA is kind of build the earliest precursors, the earliest robots that we might someday send to a world like Europa. So I'd like to share with you now a piece that was put together by Mark Thiessen and others here at National Geographic that shows you a tiny step forward in the technological development that will someday lead toward exploring Europa's ocean, but today we're utilizing to explore extreme environments here on Earth.
The rover that our team has developed is an early precursor of something that we may someday fly to Europa. The buoyant rover for under ice exploration is designed to float on the underside of the ice and rove as if the underside of the ice is the ground. These ecosystems up in Alaska, these lakes that freeze over every year and freeze down, they're just one example of life in an extreme environment that can help guide us in assessing whether or not a world like Europa could harbor life. We cut a hole in the ice, put the rover underneath the ice, and then left it out there to rove around. And we went back to the nice warm Quonset hut, and our team was even able to hand over control to engineers down in JPL. And so we think this truly was the first time ever that an underwater, under ice, untethered vehicle has been operated through satellite link. Our work has this wonderful marriage of advancing our understanding of what's happening on our own planet while simultaneously feeding forward into our exploration of potentially habitable worlds beyond Earth.
Thank you. So I'll finish. You've seen a lot of great images from our history of solar system exploration. But I'd like to close with my favorite image from the history of solar system exploration. It's an image carved by the hand of Galileo, an image carved some 400 years ago. Shown at center, you see Jupiter, and around Jupiter, you see 4 tiny little dots. Now, initially, when Galileo turned his telescope to the sky and observed these 4 tiny little dots around Jupiter, he named them the Medicean stars, the stars of Medici. And he did so because the Medici family was funding his research. And Galileo was no idiot. But as he charted the motion of these little points of light night after night, he noticed that they moved. And he began to realize that they, in fact, were not stars, but they're moons. And if they were moons going around Jupiter, then that meant that not everything rotated around the Earth. And through his careful charting of Jupiter and its moons, Galileo helped put the final nail in the coffin of Aristotelian cosmology, this idea that everything goes around the Earth. And he really opened the doorway to the Copernican revolution, this idea, of course, that we go around our sun is a star, and the stars that we see might be suns to other worlds. And in the decades that would follow Galileo, we would come to appreciate that the laws of physics apply not just here on Earth, but also to worlds and wonders elsewhere. And in the decades after that, in the centuries after that, with the development of new telescopes and new tools, things like spectroscopy, we would come to appreciate that the principles of chemistry apply not just here on Earth, but also to these worlds and wonders elsewhere. And then with the advent of the space age and our exploration of worlds like Mercury and Venus and Mars, we would come to appreciate that the principles of geology also work, not just here, but on these worlds and wonders beyond the Earth. But when it comes to the fundamental science of biology, we have yet to make that leap. We have yet to understand whether or not this bizarre phenomenon that we call life works beyond Earth. We have every reason to believe that it should. Our study of life here on Earth and our exploration of these worlds elsewhere indicate that we think some of these worlds should be habitable based on what we've learned about life here. But we have not yet done that experiment. And part of what excites me about the time in which we live is that for the first time in the history of humanity, for the first time since we've looked up at the night sky and asked that primordial question of, is there life out there? We have the tools and technology, the scientific and technological capability to do the experiment, to see whether or not biology works beyond our Earth, to see whether or not this phenomenon we know and love called life works on worlds and wonders elsewhere. And so I hope that in much the same way that we can look at this image and appreciate the revolution that was catalyzed by the observations and the research that Galileo and everyone did some 400 years ago, I hope that our descendants, some 400 years from now, will look back at our time and they will be able to say, it was then, it was during that time that humanity did the exploration, developed the tools and technology, and made the discoveries that brought our universe to life. Thank you.